everyone. So today we'll talk about electric force and electric field. Alright, so charges exert forces on each other. That's kind of the long and short of it. Alright, so we call this force the electric force. Alright, this is the way we compute what the value of this electric force is going to be is what's known as Coulomb's law. Alright, so if we wanted to compute the electric force between 2 point charges. Hi everyone. So today we will talk about electric force and electric field. Alright, so I can't actually do a demo since we're doing this video, but nonetheless. So let's go back to our example of rubbing a balloon in your hair. Alright, so when you rub a balloon in your hair, we're stripping electrons from your hair to the balloon, so the balloon becomes negatively charged and your hair becomes positively charged. If we were then to take that balloon and put it against the wall, we would notice that the balloon sticks to the wall. The wall itself is neutrally charged. So although we have a balloon that's negatively charged, it sticks to the wall, which is neutrally charged, which is pretty interesting. Now that balloon, if we brought it against our hair, we would see that our positively charged hair is attracted also to the balloon. And actually our hair would then go from not moving to moving, so it would actually accelerate towards the balloon. So we see here that we've got some sort of force going on. All right, we call this the electric force. All right, so we'll talk about electric force and electric field. So to compute the value, so this force, what we observe is that when we have objects, or just charges, as you say, if we have positive charges or negative let me start over, excuse me. Like charges repel, unlike charges attract. That's what I was just trying to say. It did not come out that way. We can compute the magnitude of the force of this attraction using something called Coulomb's law. All right, so Coulomb was a physicist back in the day who studied this, and so he gets a law named after him. So if we wanted to try to compute the electric force between 2 point charges, which what I mean by a point charge is if we had some sort of object that's charged that's very, very small, ideally just a point particle. What this basically means, if we have two charged objects whose size is much, much smaller than the distance between the two. So this formula here holds for things that are very small in size and things that are have spherical symmetry to them too. But if we have two charges and put them some distance away, if we have one object that's a negative charge, the other one a positive charge, they're going to be attractive. And if both are positive or both negative, they're going to be repulsive. So that's what these pictures here are showing. All right, use the symbol a lowercase q for charge here for our point charges. And what we notice is that the magnitude of the charge acting on each other are equal and opposite in direction. So we do have a Newton third law pair here. Electric force is a Newton third law pair. So one charge exerts a force on the other charge that is equal magnitude and opposite in direction to the charge that the other exerts on the other first. Anyway, if you wanted to compute this, we use this formula. So this formula is on your formula sheet. It says that the electric force, F with a subscript of E, the magnitude of that force is equal to K times Q1, Q2 over R squared, right? So K here is a constant, right? K for constant, since constant starts with K. Anyway, this is not spring constant. This is known as the Coulomb constant. All right, so just be careful. We're dealing with the same symbol meaning two different things. Still both constants, but fundamentally different. All right, this constant, all it is proportionality factor. If we were doing this activity in class, we would have actually done an online lab in which you would have derived this formula using graphs, so it would have been lots of fun, but that being said, you would have come up with this formula yourself in this relationship. So this proportionality constant has a value of 8.99, or I like to just use 9, times 10 to the 9 Newton times meter squared over Coulomb squared. Right? Then you you plug in the charges. So since we're dealing with a force that one charge exerts on the other, Q1 and Q2 would be those two different charge amounts. All right. And then R is the distance between the charges. Why do you use R instead of D or R instead of X? Right? R, because we do have spherical symmetry here. So for example, on the image to the right where you have this negative charge and positive charge, there's some distance R apart. If that positive charge was that same distance, but let's say above the negative charge, we would end up with the same charge magnitude, just a different direction. So that's why we're using R. We do have a spherical symmetry here going on. Right. I think that's basically what I want to mention here. Now looking at this formula, the form itself looks pretty familiar. And just thinking about the force itself is kind of familiar because we're dealing with a force here in which we're dealing with objects that are interacting with each other that are not in contact with each other. So this electric force is a non-contact force, and yet there is still a force exerted. Right? We've dealt with that kind of force before, a long-range force, and that would be the gravitational force. If you remember the gravitational force, we have a similar formula. Right? We have the force of gravity is G m1 m2 over r squared. All right, so then here in our numerator, we've got our objects interacting. Here we're dealing with mass instead of charge, but we're dividing by distance squared, distance between the objects, and we have a proportionality constant. So very similar formula to our electric force, and that's because all long-range forces are going to have this type of formula. All right, and these are also because this is what's called a conservative force. All conservative forces have this formula. We also had a somewhat similar formula when we were dealing with intensity, but we're not going to worry about that too much. All right. The AP exam is going to emphasize the similarity here between the electric force and the gravitational force. All right. But that being said, all right, let's kind of review briefly here about fields. All right. So how can an object exert a force without actually contacting another object? Right? And it does this through interaction with the field. Right? So a field is just a mathematical construct used to explain how objects can exert forces on each other without touching. Right? So basically this field exists at every single point in space around whatever we're analyzing. So if we're analyzing a charge, at every point in space around that charge, there is a field that's created by this charge. When another object, another charge, interacts with this field, it's going to then feel a force, an electric force. All right, and we can say the same thing for the gravitational force as well. That would be an object that has mass, creates a gravitational field around it, and any object that has mass interacts with that field and feels a gravitational force. All right. So with the gravitational field, right, the Earth, which is the most typical example we use for gravitational field, just because that's the force we're used to, is the force due to gravity on Earth. The Earth has some sort of mass. I'll use symbol capital M here for the mass of the Earth, and it has a gravitational field surrounding it. All right, so any object that has mass, lowercase m, so let's say you, standing on Earth, can experience a gravitational force of the Earth interacting with this gravitational field. So near the surface of the Earth, we use the formula F equals mg, right, because the gravitational field is uniform, meaning that g is 9.8 meters per second squared near the surface of the Earth. Right? Further away from the Earth, right, if you stood further away, the gravitational field is actually not constant for the Earth. So we do have to use the general form of the equation we have on a previous slide. Right? Now, some sort of terminology just to introduce. When you're dealing with the object that creates this gravitational field, we call this the source object, and the object experiencing the field is called the test object. All right. Now that being said, this test object, or you, the person here, also has a gravitational field, but it's very small compared to the source object. But we could do that analysis. So if we wanted to compute electric field, all right, we we'll then analyze, well, we have some sort of source charge, a source of the electric field, and a test charge experiencing the electric field. So generally speaking, if you're looking online doing some extra research, lowercase q means test charge, capital Q means source charge. But that notation's not too necessary to know. But the electric field is actually going to be the amount of force available per unit charge. All right, so we have our numerator here, force in newtons, and the denominator, charge in coulombs, giving us the value of the electric field. This is going to be a vector quantity because we're dealing with force, that's a vector quantity, divided by charge, which is actually a scalar quantity. Charge does not have direction. So that leaves us with a vector. So the direction of the force is the direction of the electric field. Now, this is with the definition that our charge is a positive value. So if our charge was negative, that gives us a negative sign on the right-hand side of the equation, telling us that the electric force is in the opposite direction of the electric field. All right. But again, electric fields, I'll just mention, are not a focus on the AP exam. In fact, they're not something that you have to learn. I think it's a very important concept, so I do want to introduce it. Now we can write a similar expression here for the gravitational field, and actually this is on your formula sheet. So looking at the right-hand side of the equation, we're dealing with the force associated with the field. All right, so we're going to be dealing with the gravitational force then. And the bottom, we're dealing with the quantity that we're dealing with that creates that field. So instead of charge, we'll have mass. So the gravitational field is going to be the amount of gravitational force available per unit mass. So available per the amount of mass we're dealing with. All right, so we're dealing with the force of gravity divided by mass, which you guys know is g, gravitational acceleration. All right, so another way we could express gravitational acceleration would be gravitational field, and this is kind of the reasoning behind that. So if you look on your formula sheet, they don't write it as Fg equals mg. What they write for that is on your formula sheet is written as seen here on the right. So the gravitational acceleration is equal to the gravitational force divided by mass. And the reason for that is to kind of express the idea behind fields implicitly just by writing the formula in this way, which I find to be pretty interesting. All right, so that's what I have for you guys today. In terms of examples for this lesson, I have two. Going back, they're going to focus on how to apply Coulomb's law. So we'll look at one example, a realistic situation of the electric force going on within a hydrogen atom. So we'll see the force between the electron and the proton in that atom. So computing this just for two charges then. The AP exam may also ask you what's going on with, we have, let's say, more than two charges, so 3 charges. So I do go through an example in which, how would you approach a problem in which we have 3 charges interacting with each other. All right, so there you go. Thanks for listening.